Hi.
All right, so again, a pleasant evening to our faculty, guests, and attendees for tonight. I am Jason Sam Jeremias.
And I am Ricardo Rojas II. We are your moderators for tonight's installment of the Department of Chemical Engineering Seminar Series. The department has been hosting several talks for the past year featuring our alumni, industry partners, and our research collaborators to share with the DChE community their expertise and experiences.
So for tonight's webinar, we will be featuring our very own faculty members who will share their recently published works from conceptualization to publication.
So before we proceed to our program, we have a few reminders for our viewers. Please mute your microphones and turn off your cameras while the talks are ongoing. If you have any questions during the talks, you may hold on to them or post them through the live chat features of our Zoom. We will read your questions during the question and answer forum at the end of each speaker's talk. For the live questions from our Zoom participants, please wait until we acknowledge you before unmuting, and we encourage you to turn on your cameras when you ask your questions live.
So like what I've said a while ago, our webinar this evening will feature talks from our faculty about their research and career experiences. So we invited two DChE alumni turned faculty to share their thoughts with us tonight, so let's get started. Our first speaker is an assistant professor of the UP Diliman Department of Chemical Engineering. He is also the laboratory head of one of the newest institutionalized research laboratory in the department, the Advanced Materials and Organic Synthesis Laboratory. He is also a recipient of the Balik Scientist Program of the Department of Science and Technology, which aims to reverse the effect of brain drain in the country, to strengthen our science and technology capabilities, to accelerate the flow of technologies, and lastly, to promote knowledge sharing. Here to discuss his research work on Cyrene as a Neoteric Bio-based solvent for catalyst-free, microwave-assisted construction of diverse Bipyridine analogues for heavy metal sensing. Let us all welcome Dr. Ramuel John Tamargo.
Hello. Haba, no? Title.
Oo nga, sir.
Yeah, I'm going to share my screen. So can you see it now?
Yes, sir.
All right. All right, I'll start. All right. Good evening to everyone. I am Dr. Ramuel John Tamargo, an assistant professor in the DChE. As mentioned, I am a recipient of Balik Scientist. And for today, I would like to talk about neoteric green solvents. Classical problems require modern solutions. So I guess some of you can see the reference that I did here. Well, if you don't, then later I will show it to you. All right. Right. In 2005, they have the ACS Green Chemistry Institute Pharmaceutical Roundtable. They have has been developed. So what they did here is they have formulated different key research areas in green chemistry, because the problem usually is there is a disjoint between what the researchers has been doing and the need of the industry, especially for the pharmaceutical industry. So they have started with 5 members, and then last 2016, they have increased their membership into 15 members, and then they have formulated these key research areas. So I think you can notice some of familiar names here, like AstraZeneca, Pfizer, Bristol Myers Squibb. So they have formulated this so that it can be a guide to us researchers what to do. So these are they have formulated this. So for the key green chemistry research areas, here are the 10 research areas that they have developed. So those with asterisks are the new research areas. So as you can see, every year or after a few years, new technology are needed for the pharmaceutical industry to move forward, because of course there are many developed methodologies, and then the previous problems has already been solved. However, if you can notice, some of those that doesn't have this asterisk, they are already problems before that still left unsolved. And while some of these key green chemistry research areas has been shuffling since they are being um, established through a votation. So they have also formulated this solvent teams, which the viable replacement for polar aprotic solvent. On the other hand, for the halogenated solvents, it is treated as a new research area. But for the number one, it has been a long-standing problem. But still, the researchers hasn't been able to solve this. So they were not able to offer an effective green alternative for this class of solvents, right? So as you can see here, the GSK has published their solvent sustainability guide. So as you can see here, there's an area of the sustainability guide that's left unfulfilled, which is this. So as you can see, for the hydrocarbons, ethers, and dipolar aprotic, they do not have any alternative for problematic solvents such as DMSO, acetonitrile, DMF for the dipolar aprotic. So while some of the solvent classes, they don't have any alternative as well, like hydrocarbons, but in pharmaceutical industry, they mostly use dipolar aprotic solvent due to its effectivity in doing nucleophilic substitution and its solubility to the substrate, because hydrocarbons are usually especially those are strictly hydrocarbon, they are non-polar and they have problems in solubility in terms of the substrate when you try to keep different type of reaction, especially the nucleophilic substitution reactions. So why solvent? So solvents, they account for 80 to 90% mass used for active pharmaceutical ingredients. It means that that's like the ratio. They use the substrate is just like 10%, but they use this much of solvent, and these solvents are going into waste, right? And thus they constitute more the majority of the waste in the pharmaceutical industry. And for dipolar aprotic solvent, they mostly use those that coming from the petrochemical industry, and most of these are usually unsustainable and highly toxic. That's why for this type of solvent, the pharmaceutical industry is indeed in dire need of a good alternative. So one fellow of the Royal Society of Chemistry, Roger A. Sheldon, who is also a pioneer of green chemistry, he told about more than 25 years ago that so many of the solvents favored by organic chemists are now on the blacklist, that the whole questions of solvent in organic synthesis requires rethinking. Not only do organic chemists generally use too much solvent, they often use the wrong ones. In the first place, why do we even need to use solvent, right? While we can use just water, right? So it could be a layman question, but also at the very core of chemistry, if we can use water, that's the ideal solvent because it's easily replaceable, it's non-toxic, right? And it's very easy to handle. But like he mentioned, this he was able to say this 25 years ago, but the same problem still happens today. So why not water? Okay, because we have generally we have two types of solvent. First is the non-polar solvent and the polar solvent. For the non-polar solvents, we have benzene, mesitylene, and also N-hexanes. Other non-polar solvents include Cyrenes, okay? But this type of solvents are generally used in the polymer industry, and usually they are not being used in the pharmaceutical industry. That's why the pharmaceutical industry doesn't really care much about this type of solvents. Meanwhile, for the polar solvents, we have the polar protic solvents such as ethanol, aniline, water. So some of these are sustainable, some of these are generally safe, but of course there's still a mix. But still, you have a good alternative for this type of solvent. However, for the dipolar aprotic solvent, we only have this DMSO, DMF, acetone, ethyl acetate, and NMP, which are all health hazards. Okay, so the problem is if you use this type of hazardous chemicals in trying to synthesize drugs, as chemical engineers, we already know that it's very hard to remove, right? So so in our case, it is really in our benefit to develop a new type of solvent. But of course, as I really believe that like organic synthesis, mostly many researchers have already mixed everything that is that you can think of, right? So we really need a new, basically a new molecule or a synthetic derivative of some biomass, for example, so that we can try other solvents. So in this case, these are the dipolar aprotic solvent used in the literature. As we can see here that DMF is highly used here. Here, DMF and acetonitrile, and most of them are still problematic, including DMSO. Okay, so while we have for the dipolar aprotic solvent, we have some generally safe like ethyl acetate, but these ethyl acetate have are very volatile. So for those that needs a higher boiling point, we don't really offer any good alternatives, and thus we have found some candidates here like Cyrene, Polar Clean, and NBP here. Cyrene, Polar Clean, and NBP. So as I mentioned, most of them have already some greener alternative. Okay, most of the classes except this one. So how did I stumble upon Cyrene? Okay, I think it is somewhat a coincidence because I just happened to be subscribed in CNN, and then I just like reading articles. So I think this is one thing that you can, as a new researcher, even for seasoned researcher, you always have to read because you have to know what happens all around us, right? So you will know that there's a new technology being developed or new chemicals that are interesting chemicals. And then I happen to stumble upon this article which talk about Cyrene, which want to be a better alternative to NMP. And NMP and the MSO are highly toxic, and I really find it to be interesting. I even printed this article, and then I showed it to my professor that time. Then I told professor, I think we should buy this Cyrene, and I want to keep some reactions that could, maybe we could develop some new reactions that use this Cyrene, and I think it's already beyond novel because it's a new reaction and using a new solvent. I guess it's it's a perfect combination. So Cyrene actually is a also somewhat like an experimental product because there's a paper company, they want to improve their line of products because of due to something optimizing their business. So they want to develop a new derivative of cellulose. Okay, so they have this product LGO, and then there's a consultant that said maybe we could try to hydrogenate it and let's see what happens. And they were able to get Cyrene out of it. And then this Cyrene happens to be a good solvent for that can be used as an alternative with DMSO and NMP. So, and then they try to keep some reactions, although some conditions proving to be problematic, especially with the presence of base and presence of some nucleophiles. But still, they were able to show that it's promising. Okay, so then, as I mentioned, the Cyrene have similar properties with NMP and DMSO, and it is biorenewable because it has been developed from cellulose. It also have high thermal stability, and it is highly compatible with water. So it's easy to do workup. It's easy to remove from the reaction. It can also be recovered from the reaction. So it's like a perfect combination. But still, it has its own drawbacks. Okay, so I use this to synthesize pyridines. So why pyridines? Because pyridines are very interesting scaffolds. Like they, most of them can be found in as active ingredient, right? Even the pyridine itself is very interesting, right? You can see many pyridine rings in different drugs and in different natural products. And the synthesis of bipyridines has proven to be very challenging because of the presence of N. So previously, they use traditional coupling methods to obtain this type of pyridine. So mostly a pyridine with another pyridine, okay, with different conditions, okay. And then if you need to synthesize 2,2 or the one with in the 3 position, and then in the 4 position, you have to use different type of pyridine. But those pyridines are also hard to obtain, and also it is hard to match everything because what if you can just get a dimer product, right? So in this case, I have found a solution that uses amine, formylchromones, and then this benzyl cyanides. So in this case, these pyridyl acetonitrides were used to in situ make this pyridine ring, and then the attached pyridine ring can be found after the formation of while the pyridine ring is being formed. So that's the strategy that I have developed, and I have used here Cyrene in microwave irradiation at 130 degrees Celsius. And the good thing here is all of these atoms are being used, and the only byproduct here is water. So I don't have any waste products. I don't have any elimination products that are could be also harmful. All right. So here, so I have used a different mix of amines, formylchromones, and benzyl cyanides. But I have first optimized this reaction condition. So I would know that, all right, this is the best condition before I get to check the scope of the reaction. So first, I try this in a clean condition without any solvent. Okay, because that's the most ideal condition. You don't need any solvent. You just heat it and just allow it to form. Yes, the product has formed, but albeit a somewhat poor yield. And then I use and I tried to use different type of solvent, but I didn't get it with water, and I found out that in DMF it is I'm getting moderate yields here, DMF at 66% yield. Now I found that maybe I can try with Cyrene, and then with Cyrene I was able to increase the temperature And so I was able to optimize the yield of this product up to 94% yield. And then I found that 130 degrees Celsius is the best temperature for this, because more than around 150, the Cyrene starts uh, to decompose, and there are other byproducts that can be formed. That's why, especially if you try to keep it at 24 hours, the self-condensation of Cyrene can also happen. So here I have confirmed that this is the target structure. I use IR, I use NMR, I use HRMS to confirm the structure of this product. And for this proton NMR, we can see here that this singlets, we have two singlets here that correspond to this this lone protons in the center pyridine ring. We can also see the OH here, this OH, and this amine here. Okay, this OH is somewhat around 12 because it's there's a hydrogen bonding, and this NH sometimes can shift from around almost 13, sometimes 11, depending on the water content, depending on many factors. But mostly we have fixed this OH bonded hydrogen bonded OH around 12. Okay, and this corresponds to the correct number of protons. And then you can also see here this confirm this 5G using carbon NMR. So we can see also here it's pure one, and then we can see the carbonyl here. Okay, and around this 150 to 160, those carbon that are near to the nitrogen. Okay, so I have also further confirmed the structure of 5G using X-ray crystallography. Okay, and then after confirming it, I was able to try it using different aniline. Okay, I tried to use different aniline. So I was able to obtain these 9 products in excellent yields. So I was able to synthesize it with electron donating groups and halogen electron withdrawing groups, also in different positions. Okay, so I was able to confirm that it is robust using different anilines. Okay, I have also tried it with different amines. Here, different amine. So not just aniline. So I was able to get this type of products, even with this cyclic products, and also some with chains. Okay, some with benzyl, and also with different type of steric hindrances. Okay, because this type of products are somewhat challenging to synthesize. Also, I have tried it with different cyclic groups. This is also another pyridine. Okay, another pyridine, and this this I have mentioned that I have able to get this structure. Okay, now that I have established the generality with the amine, now I have tried with different hallmark hormones. This one, the blue one. Okay, I have tried with different hallmark hormones, and I have used here with different donating groups, different electron withdrawing groups, even if in combination of it, even with 2 electron withdrawing groups, and even with the extended conjugation, I was able to synthesize this bipyridine in excellent yield. Okay. And then the final one, the pyridyl acetonitrile. So in this case, I wanted to obtain not just the pyridine in the 2 position here, but I also tried with this one, this 3B and 3C. And fortunately, I was able to obtain that. So here, I was able to get this 7A here in 70% yield, along with a combination of another chromone. Also this 4 position, okay, or para position here, and with a different amine. So we can see here that it's still flexible or robust. Now, what if I will not use a pyridine here? So I also tried it with just benzyl cyanide. But unfortunately, or fortunately, both unfortunately, I'm able to obtain my desired products. However, I need strong electron withdrawing groups here. As you can see here, cyanide, nitro, dichloro, trifluoromethyl here. But using just benzene, benzyl cyanide, and with this electron donating group, I was not able to get my product. So what happens? So I need a strong electron withdrawing group here to activate this position so that I can make the actual ring. So I have kept some control experiments to prove my proposed mechanism. So first, I have kept this reaction using my standard substrate in room temperature with Cyrene. So I just got this 7. So this is the combination of 1A and 3A. So as you can see, and then I used this 7. I added aniline, and then I tried to heat it, and then I was able to get my final product. Okay, so I was able to prove that this is my intermediate. Okay, so this is the reaction proposed reaction mechanism. So from the pyridyl acetonitrile in basic condition, you can get this 3A prime, and this 3A prime will now then attack the 4-micromole. Okay, and in Knoevenagel condensation, after the formation of this elite, and then the proton migration here, this proton, we will get this intermediate 2, and then this intermediate 2 happens to undergo dehydration to get this intermediate 3, which I was able to get here. See, and this 7 can then undergo nucleophilic addition with amine, and getting this intermediate 4, and then now the ring closing mechanism happens, intramolecular Michael addition, and then the ring opening produces the final product. Okay, so that's why we have this OH here, because of this cleavage. Okay, so I was able to prove this using the control experiment, and now I tried to use it because I found that there's so many active sites. So I think it's good for metal sensing. And then we tried to screen it, and we have found that it is sensitive in detecting mercury, iron, and copper. Okay, and we have tried these 2 representative compounds, 5G and 6J. And we expect the 6J has somewhat better response due to its extended conjugation in visible area, in visible region. Okay, so we have, this is our proposed method of complexation. So we have tried it, and we have checked the response of 5G in different concentrations of mercury, iron, and copper in the PBS buffer solution. So we can see that it is responding well to the increase of the concentration. Okay, similar with the 6J as well. So 6J also respond to the increase of mercury, iron, and copper. Okay. And as a visualization, this is a sample of the photo of the increase of concentration of copper, iron, and mercury in 6J, the one with extended conjugation. As you can see, as we increase the concentration of copper, we can see using the naked eye that there's a color change. However, maybe you can ask why the silver doesn't change much, but still the equipment can read the change here. So maybe if you can ask if it can be a colorimetric sensor, we can use it with copper. Okay. So this paper has been published in ChemSusChem with this title. So I would like to thank my co-authors, Peter Rubio and Dr. Ojandos and Professor Jaden Chim and my professor, Professor Yong Rockley. So for the future works and collaboration, I have talked with Dr. Jason Camp, which they are the provider of Cyrene, because I wanted to do more Cyrene work. And we have talked to him and with the initiative of my student as well. They have presented to Dr. Camp and they were able to provide us some solvent, but this work has still somewhat become pending because of the pandemic. So we were not able to start much of the proposed work, but I'm really excited to start this. So another future work is our Cradle project, our NICER program entitled Center for Environmental Technologies and Compliance. So this is under the program, our program leader here is another Balik scientist, Dr. Abisi Dandres from PUP. And I am leading one project under Air Saver. So this is another work that, under the theme of green chemistry and environmental engineering. Here we want to develop some absorbent that will remove VOCs from the plastic industries. Okay. So before I will end my presentation, this is the reference. This is the reference from my presentation. Here, Dave Chappelle said, "Modern problems require modern solutions," but I would say classical problems also require modern solutions. Okay. So then I would like to acknowledge UP, Diliman for being my host institution in Balik Scientists. College of Engineering, DChE, and Yongnam for the collaboration. And I would like to thank also DOST Pishart, and the DOST Balik Scientist program for giving me the opportunity to be engaged. Okay. If you have further questions, you can send me an email here at my email and in my contact using the QR code. All right. I hope you learned something from my talk. So I'm open for your questions. Thank you.
All right. So thank you very much, Sir Ram, for your very comprehensive talk and for expounding the need why we have to devise modern solutions to some of our classical problems, especially in this setup, the choice of solvents utilized in the pharma industry, given that 50% of the waste from the said industry is actually from the solvents. So it is also fascinating, how Dr. Tamargo thought of Cyrene as a substitute solvent for this type of application. He just basically saw it from an article, and from there he proposed this novel way of production of several bipyridine using the bio-based Cyrene solvent. So if you have any questions for Dr. Tamargo, you may send them in using the live chat features of Zoom. For live questions via Zoom, please use the raise hand feature and wait until I acknowledge you before unmuting. I encourage you to turn on your cameras while asking your questions live. So, all right. So for our first question, sir, you have mentioned the optimized reactor conditions, which gives a good percent yield for the reaction you mentioned. So I was just wondering if these conditions are also applicable in the industry setup.
Yes. This is very compatible with the industry setup since many processes, especially for the peptide synthesis and other drug synthesis, this type of condition around 130 degrees Celsius is natural. And but I think one challenge here is the application of microwave in a larger scale. So many researchers are still trying to establish microwave as yes, it's a good lab scale setup, but you know something that will translate it into an industrial scale will make it really feasible.
All right. Thank you very much, Sir Ram. So next question. How long did it take you to do the synthesis experiments? What were some challenges in conducting these? Also, did you explore high throughput methods?
Actually, it took me like almost 2 years. I read this paper. I think it was published around 2019. But I was already working on my synthesis, and I just found that this Cyrene solves the problem. And in terms of doing a high throughput synthesis, it's really hard to make a high throughput synthesis if you're doing a novel reactions. Usually, you can use more established methodologies because they have simpler setups and they have high yields already. But in my case, since I really need to check every reaction if they're going or not. Um, so somewhat I'm really my pace has slowed down drastically because of that. But since the microwave reactor that I've been using can use like around 8 altogether. Sometimes I'm just when I'm trying to screen the conditions, I can do everything all at once and then check which condition actually worked. But in terms of trying another substrate, you don't. It's really hard to do it all together, especially if you're just still doing some tweaks here and there.
All right. So thank you, Sir Ram. We have another question from our Zoom participant. Were the radiation hazards manageable since you are using microwave assisted production here? And how would this scale in mass production?
Actually, I'm already using a big microwave reactor. So in terms of doing it in a big amount, I've already did gram scale synthesis of this, which I included in my paper. And I think, yeah, like I mentioned, I can make it a bigger scale, but not really an industrial scale because we don't really have that kind of microwave. But in terms of the radiation risk, it's like using your tabletop microwave. You can heat your food without being scared of the microwave radiation because it's basically a closed reactor. So it is designed that no microwave can escape from the equipment. So it's basically a safe. Actually, it is safer than traditional one. Instead of just heating using
Yeah.
a hot plate,
Hmm.
I believe that microwave is even safer.
Okay, sir. Meron na daw ba, sir, microwave sa lab niyo?
Ah, with the recent approved project, now I plan to buy one microwave reactor.
Okay, sir. Okay, so next question. You mentioned that this can be a possible chemosensor. So how this will look like as a possible chemosensor? Could it be embedded in a paper like the litmus tests?
Yes, since it is shown to be a good uh, candidate for colorimetric test. We can make paper-based sensors out of these molecules. Um, the the challenge I think is some ions like mercury, they have low limit of detection, and thus we cannot really do it in a naked eye test. But some ions like copper, we can make paper sensors out of it. And our test, we did it in under PBS buffer, which is a step in trying to prove that you can use it in biological systems. So if we can develop it into such a way that we can detect a high amount of metal ions in the blood, for example, then hopefully we can use this technology into another type of sensing. But mostly what I had in mind is just to detect the heavy metals in the aqueous systems, and you know before translating it into another application.
All right. Thank you very much, Sir Ram. So I think we can cater at most two more questions. So we have one question from our Zoom participant. It is fascinating how the choice of good solvent has been narrowed down among all the available potential solvent. So she's asking, how have you veered away from a potential trial and error setup from among all the potential solvents?
Mm, um, Usually, you have already identified the type of the class of solvent. For example, you have identified that it works using a polar aprotic solvent. So your choice will be also under that same category, right? You will not just use more non-polar solvents just to try and optimize the reaction, but you already know the chemistry, so you already know what solvent is good with this type. And then in terms of using a greener alternatives, I didn't use the polar clean. I haven't used other alternatives yet because I'm just wanted to prove that Cyrene is a good alternative.
Okay, thank you very much, sir. So I think to end this open forum for your session, uh, were you or your laboratory able to pitch in this concept of Cyrene as a bio-based alternative solvent in some pharma companies that might uh, use it in their processes?
Um, yeah, that's why our group pitched the project to Dr. Jason Camp,
Yeah.
because we would like to synthesize asymmetric sulfides, which are common scaffolds in drugs, and we want to make a clean synthesis using Cyrene and other scaffold as well, even peptide synthesis. We wanted to explore peptide synthesis using Cyrene, but to the industry, not yet.
All right. Thank you again
That's
to
it.
Doc. Yes, sir. Okay na po.
Hello.
Hello. Ayan. So again, thank you very much to Dr. Tamargo and to everyone who asked or posted questions. So let me turn you over to Mr. Ricardo Rojas II, my co-moderator for this evening. Mr. Rick?
Hi, okay, so our second speaker is an assistant professor in the UP Diliman Department of Chemical Engineering. She is the laboratory head of the Laboratory of Electrochemical Engineering of the department and our new department chair. For tonight, she will be talking about the highlights of her paper entitled Unravelling the Roles of Alkali-metal cations for the Enhanced Oxygen Evolution Reaction in Alkaline Media, published in Applied Catalysis B Environmental. Let us all warmly welcome Dr. Julie Ann San Jose.
Anne del Rosario po. Julie Anne del Rosario.
Oh my God, apologies po, Julie.
No
Julie
worries.
talaga.
Wait. So, good evening, everyone. Yeah. Can you clearly see my screen?
Yes po, ma'am. Yes, ma'am.
Okay. Ayan. So, thank you for the introduction, Sir Rick. So, as mentioned, this is a recently published paper in Applied Catalysis B. So, this is also part of my PhD dissertation. And tonight, I will share how we conceptualized this paper and how we were able to publish it. So medyo actually personal story ko yung laman nito because of how we were able to publish finally itong dissertation paper ko. So just to start, let me just share to you my PhD journey and how I learned that not everything goes according to plan and it's actually okay. Ayan. So just to give you a background of my PhD plans before, when I entered the department, I already graduated from my MS. So yung next step ko is to take my PhD. That time, since I am an MS and Visay and graduate, feeling ko kulang ako sa math courses as compared dun sa pino-project in the PhD DChE program. So what I did to improve myself is to take more math courses in PhD DChE in the department without the plan to finish in the department. So may plans talaga ako to do my PhD in South Korea kung saan din ako nag-MS. So I plan to go back to the same laboratory. So ito talaga yung PhD plan ko and actually I got accepted in the same lab in Korea and from then I am planning to graduate in 2019. Ayan. Pero actually hindi naman talaga yun yung nangyari. So what actually happened is due to some personal reasons, I was not really forced. I chose to continue my PhD in UP Diliman. So nag-start ako ng 2014, so kinontinue ko siya noong 2015 and then I followed yung plans ko until I was sent for a sandwich program in the US. So I did most of my experimental work in UC Merced despite na local PhD yung kinukuha ko. During that time, because of what happened, I will show you later kung ano nangyari dun sa proposal ko. And due to the environment tsaka yung advice of my US professor, so I had to change my PhD dissertation topic. And then after a year, so 8 months yung sandwich program ko, I was able to defend my dissertation. Actually, so 2019, after my defense, I was able to graduate even though hindi ko pa na-publish yung dissertation ko. So later pa, tsaka, which is this year, tsaka pa lang na-publish yung ginawa ko nung 2019. So, ayun. So, I know that this is not the ideal PhD journey, but somehow I made it through. So, kaya parang relief din na na-publish na yung PhD dissertation ko. Yan. So, I think one quote na nagsasummarize ng PhD journey ko is this one. Sometimes the wrong train will get you to the right station. So I first saw this quote from a movie, yung The Lunchbox. So para dun sa iba siguro, napanood nyo rin to sa Chloe. So it's from the movie The Lunchbox. Sometimes the wrong train will get you to the right station, which is actually true. And it's actually, for me, it's okay. Ayan. So, since I will share to you kung paano na-publish itong paper na to, I will just go back to the most exciting part ng aking PhD, which is actually selecting my research topic. So, si Sir Joe yung advisor ko in 2015, but he just returned also from his PhD. So, because of that, I have more freedom, less restrictions in choosing a research topic din. Kasi hindi siya limited by research projects, ganyan. So, mas malaki yung chance ko to choose my own research topic, which I actually enjoyed. Meron akong full page of possible topics na pinresent ko kay Sir. Of course, most of them were crossed out eventually. But yung mga research topics that I have written down actually came from my skill sets. So kung ano yung alam ko na. So since I came from an electrochemical reaction and technology lab from my MS, so doon ako nag-focus on my skills, which is mostly on electrochemistry. So since electrochem kami, nagpo-focus kami on redox reactions, which are pair of reactions. So I know for a fact that yung oxygen reaction are usually the rate limiting reaction for most electrochemical processes, such as in fuel cells and in advanced batteries and in electrolyzers. So doon ako nag-focus doon sa pagpili ko ng research topic. And then that time, I'm also highly interested in joining research for production ng fuel cell cars. Yun talaga yung dream ko dati. Nung nag-start ako ng PhD to be part ng research group for development ng fuel cell cars. So, and I also know that time na nagpe-prepare kami ng research project for fuel cell applications. So, tamang-tama yung research topic ko for the plans nung binibuild naming laboratory. So, there will be funding for the research topic that I will be choosing. So, yun yung mga kinailangan ko for selecting my research topic. Yeah. So, from there, I decided to focus on the catalysis for a particular oxygen reaction, which is the oxygen reduction reaction, which is half reaction for fuel cells. So, yung paper later is actually oxygen evolution. So, but I actually started from the oxygen reduction reaction. So, yung una, I am focusing on the catalyst part for an oxygen reaction. So, among the different catalysts, platinum yung most suitable for ORR or oxygen reduction, but because it's expensive and prone to carbon monoxide poisoning, so we are looking for cheaper alternatives. And among the possible alternatives are transition metals and the heteroatom dope carbon catalyst. So initially, nag-focus ako dun sa heteroatom dope carbon catalyst with graphene as my chosen carbon base. And then I planned to dope it with heteroatoms. Yeah. So while doing my review of related literature, I used or studied density functional theory papers to look at different types of dopants and to see what are the criteria needed for choosing the dopants for ORR. So by RRL, I found that the electronegativity plays an important role. So here, the electronegativity of carbon is actually 2.55. So when I compared the electronegativities of the dopants in literature, for example, nitrogen, this one has a higher electronegativity as compared to carbon. So this nitrogen draws bonding electrons towards itself. So what happens is napupunta sa kanya yung electrons and then it creates positive charge densities dun sa mga nearby carbon atoms. On the other hand, kapag naman yung dopant ko will have a lower electronegativity as compared to the carbon, so the carbon becomes more negative, and then yung positively charged dopants naman, sila naman yung nagiging active sites. So the positively charged atoms becomes the active sites for ORR. And then if they have both have the same electronegativity, so usually yung mga dopants na yon are larger in size as compared to carbon, creating disruption dun sa size or angles of the carbon structure. So based on sa mga studies na yon, so I realized that for choosing the dopant, it should be able to break the electron neutrality of the graphene to create charge sites, or it should be creating steric or geometric effects on the graphene surface to be able to create active sites. Ayan. So yun yung naging basis ko for choosing my dopant. Ayan. So since meron na tayong criteria for choosing the dopant, I looked at the periodic table, and the following non-transition metal elements have been studied as dopants on carbon for ORR. But since as a PhD student, I am looking for unexplored dopants for ORR applications. So I wanted to extend itong group na to another part ng periodic table. So what I thought then is, why not try the other elements that have lower electronegativity than carbon and have larger atomic sizes than carbon. So kung titingnan nyo sa periodic table, that refers to the group dito sa left side niya. So we thought, why not try alkali and alkaline earth metal as dopants for graphene and look at their activity towards ORR. So to the best of our knowledge then, wala pang nag-explore nito for ORR application. So this would have been a good topic for my PhD dissertation. So that's what I did when I went to US for my for the sandwich program. So I prepared the alkali-metal dope and alkaline earth metal dope graphene and used them for ORR applications. So initially, meron akong proposed methodology, but eventually I had to use 3 other methods and then compare their results. I actually succeeded naman in producing the doped graphene, but I was limited to only one type of alkali metal, which is yung potassium. So I produced potassium doped graphene based on the SEM images. So we were able to create yung multi-layered graphene, and then we were sure that we have the dopant there because of the change in the structure. So if there's a dopant, nagkakaroon ng mga agglomerates on the surface of the graphene layer. Yan, as compared dito sa A. Yan. And then we were also we also proved using XRD that the presence of potassium in the form of since KCl yung ginamit naming pang dope for on the graphene material. So nakita naman namin yung presence ng potassium on the dope graphene. So this one is the plain graphene, tapos nagkaroon ng potassium peaks after doping. However, when we already tried using them for ORR application, we found the following activity. So this shows you the current density versus the potential for different synthesized graphene materials and dope graphene materials. So GR yung graphene, and then kapag may KCl, sila naman yung may dopant. And then platinum carbon, since it's the best catalyst so far for ORR, was our baseline. But as you can see here, sobrang layo ng activity ni platinum as compared to our synthesized materials. Although an interesting thing here is that we were able to increase the activity as compared dun sa plain na graphene oxide. Yan. So yung mga synthesized naman, mas mataas naman siya kaysa dun sa plain, but still, that's lower activity as compared to the baseline platinum. Also, we checked the mechanism for ORR using our synthesized materials. So this is the Kotecki-Levy plots. The important thing here is that we apply different rotation speeds to our electrodes, and then we took the current densities at different potentials, specifically dun sa lower potentials where there is high current. And then from there, using the equation, we can now get the number of electrons transferred. So usually for oxygen reactions, for yung complete na direct electron transfer, complete electron transfer. But as you can see here, we have very low values of N, which suggests a multi-step pathway for our ORR mechanism. So we actually got undesirable results in terms of the mechanism. So yeah. So for this part, we were able to successfully synthesize our doped graphene, and they perform better as compared to their undoped counterparts. However, the current densities that we have obtained are not enough for practical applications. So medyo dito nag-start yung anxiety dahil during PhD tapos na yung proposal mo doesn't show the best results that you have hoped for. Ayan. So since nandun pa ako sa US that time, and I still have time even after finishing yung experiments ko, so we decided to do another research work. So yun yung, kaya napunta ako ngayon dun sa oxygen evolution reaction. So OER is the reverse reaction of ORR. So in this case, we also need to improve its kinetics because it's another limiting reaction for electrolyzers naman, which is the opposite of fuel cells. So when we try to improve the kinetics using catalysts, we focus on the what happens at the electrode-electrolyte interface. So at the electrode-electrolyte interface, so of course you have your electrode and your electrolyte. So most of the studies focuses mostly on the electrode or the catalyst, but in our case, we try to look at the role of the electrolyte, which is less understood. So in particular for alkaline media, there is lack of understanding of what happens with the electrolyte ions on the interface. So as you can see here, kapag alkaline, it actually involves yung ions natin, the anions OH in the electrolyte. So on the other hand, the cations, so usual solvents natin, electrolyte solvents natin are KOH, so the hydroxides, alkali-metal, and hydroxide. So the alkali metals in those cases are expected to behave as spectator ions. So when a metal is immersed in the solution, an electrical double layer is formed. So we have here the charged metal followed by the inner Helmholtz plane, where specifically adsorbed species such as the reactants, intermediates, and others are located. And then we have the outer Helmholtz plane, where the hydrated ions are found to counter the charge build up on the electrode surface. So what we did is to look at different electrolyte solutions, make use of different electrolyte solutions, in particular KOH, NaOH, lithium hydroxide, and cesium hydroxide. Yeah. And then we observed what happened at the electrical double layer, and then compared it to the OER performance and proposed a mechanism on the effects of the cations. Yeah. So we made use of, again, the cyclic voltammograms, which is the current density versus the potential in the different electrolytes. So here we can see that we have two redox peaks corresponding to the pseudo-capacitive transformation of our chosen catalyst. So instead of the platinum, for OER, we have used iridium hydroxide. So siya naman yung baseline catalyst natin for oxygen evolution reaction. So we have two peaks for different electrolyte solutions. Dito pa lang makikita na natin that the type of alkali metal actually does have an effect on the OER activity. Okay, so these peaks are actually due to the adsorbed species on the surface of our electrode. So in particular, for lithium hydroxide and sodium hydroxide, the second peak are suppressed. So it becomes smaller as compared to the other types of alkali metals. And then the surface for OER is most likely the quasi-amorphous hydrous form, IROH3 and IROH4 phases, which is an important observation because the higher oxidation states are found to be the active sites for OER. So aside from using the cyclic voltammogram, we take a look at the linear sweep voltammograms. So to focus more on the activity using the different electrolytes and to focus on oxygen evolution reaction. So this shows here, so the higher the slope, the higher the activity for this figure. On the other hand, dito naman sa kabila, this is your TAFL plot. When you have lower slope here, you have higher activity. So for the for this graph, we can see here the overpotentials. So that means the potential needed for the reaction to start. So for KOH and cesium hydroxide, so it starts at 1.48 volts, but it is then followed by sodium hydroxide and lithium hydroxide. The activities in sodium hydroxide and lithium hydroxide are lower as compared to the first two, so KOH and CSOH. So the high TAFL slope, here the black one, for the lithium hydroxide suggests that there is kinetic overpotential losses in lithium hydroxide when we use lithium hydroxide as our electrolyte. So meron tayong mga kinetic losses which reduces the activity. So also from the values of the TAFL slopes, it suggests that a second electron transfer is the rate limiting step or rate determining step for the lithium hydroxide, where the dissociation of the OH bonds probably occurs. So this agrees with our initial data where the suppressed oxidation states lead to lower OER activity. So we hypothesize that this is due to the higher EDL capacitance values, and from here, we are now sure that the cations in the electrolyte definitely have an effect on the activities. Yeah. So to explain, we propose the following explanation based on the hydration energies of the cations. So when we have higher diameters for our cations, that results to lower hydration energies. So, yung mas maliit naman na cations, so mas mataas yung kanilang hydration energy, which is the energy that is released when they are hydrated or when water molecules attach to them. So, from here, it has been well proved that oxygen evolution reaction in basic condition involves the dissociation of our hydroxide bond. So that is considered as our slow step, yung dissociation ng ating OH bond. So here in our proposed mechanisms, there's a difference when we have a large cation as compared to smaller cations. So yung smaller cations involves the lithium hydroxide electrolyte, and then larger cations usually are for potassium and cesium hydroxide. So as you can see here, when we have a larger cation, it is fully solvated, so it is completely filled with the water molecules, and thus it results to formation of OH. These are the OH ions on the directly adsorbed on our metal. So they form complexes with the water molecules. Yeah. However, if we have smaller cations, because they are not fully solvated, so the cation themselves directly adsorbs or are directly connected or interacts directly with our OH that are adsorbed on the metal. Okay? So kapag maliit yung cation natin, meron siyang direct interaction with the OH that are adsorbed on the metal. On the other hand, kapag naman larger yung cation natin, there's a water involved in the complex. So from here, as hydration energy increases, the cation OH adsorbed interaction becomes stronger. And the OH, we hypothesized or we proposed that the OH stabilizes the complex, hindering OH dissociation, and it blocks subsequent adsorption of OH. And thus, the smaller cations shows lower OER activity. Since they are interacting, so this results to the stabilization of the OH, so they do not dissociate, and therefore it does not proceed to oxygen evolution. Yeah. So that's one of the highlights of our paper. Aside from that, we wanted to get a quantitative measure for our observations. So we also calculated for the EDL, or the electric double layer capacitance, using cyclic voltammetry or the single point CV method. Yeah. So here we have actually showed that the EDL capacitance value can be a measure of the charge accumulation and electron transfer rate. Okay. So this is computed at a region. So ito yung potential na wala pang OER. So there's only capacitance here. And then after that, we choose a particular point or potential, which is 0.9. And from there, we plotted the values at different scan rates. And then we calculated for the slope. Okay. So here, upon calculating the EDL capacitances, we have shown that the larger cations resulted to higher EDL. And this actually can mean that there is higher surface charging. So therefore, higher OH adsorption and higher electron transfer, which is a good for OER activity. So the EDL capacitance can be associated with the electrochemical active surface area, which in turn can be related to activity. So because of higher EDL capacitance, the larger cations provides higher OER activity. So another highlight of the paper is the use of the EDL capacitance as a measure of the activity of OER using different electrolytes. And then we used another method, which is the electrochemical impedance spectroscopy, to measure the individual resistances to point out the contribution of the cations. So different resistances include the ohmic resistance because of the presence of the ions, and then the charge transfer resistances here. Okay. So yung isa, because of interactions, ionic interactions, and then the other one involves the non-covalent interactions or the charge transfer resistances. So the ohmic resistance decreases with increasing cation size, which is actually because of the ionization of the ions. So each type of electrolyte has different ionization energy. So this is expected that the ohmic resistance will decrease with increasing cation size. And then the charge transfer controlled reactions are observed for all cases as shown by the arcs. So habang nagiging circular siya, so mas nagiging dominant yung ating charge transfer resistance. And then there's no mass transfer controlled region observed. So when we plotted the simulated resistances values, so we compared them and found that the polarization resistance or the charge transfer resistances are more significant as compared to the ohmic resistance. So so far, the smaller cations not only stabilizes the hydroxides on the surface, but they also affect the absorption-desorption of reaction intermediates or the hydroxyl radicals. And then the reason for the high activity when we use potassium hydroxide is because it has low polarization resistances or the charge transfer resistances, which leads to higher OER activity. So the trend also for the polarization resistances correspond to the trend in OER activity. So this means that the polarization resistance can also be a quantitative means to predict yung ating OER activity. Okay. So we did all the tests in iridium hydroxide, iridium oxide as our catalyst, and to check whether it only happens for one type of surface. So we also did the same set of experiments on another oxide surface, which is nickel cobalt oxide. And we have shown that the results show similar trends with that of iridium oxide. Okay, so same sila ng observed trend that lower activity is found with low diameter na cations. So pinakamataas pa din if we have larger cations, and therefore our proposed mechanism can also be applied on other surfaces. So in summary, for this part of my dissertation, so we use the electrical double layer structure and the interfacial interactions to illustrate the influence of the alkali-metal in the electrolyte of alkaline oxygen evolution reaction. So we have shown that they are similar. Similar results can be found for two metal oxide types, and that the sequence is lithium hydroxide, sodium hydroxide, cesium, and then the potassium hydroxide will be best as electrolytes for our oxygen reactions in alkaline media. So the trend are mostly because of the interaction strength of the specifically adsorbed OH intermediates, and then the non-specifically adsorbed alkali-metal atoms adsorbed in the EDL. So in particular, because of the superior activity of K+, it actually breaks the limitation of the linear scaling relation in the alkali-metal group. Okay, so it results to activity enhancement. Yeah. So this work is actually published in Applied Catalysis B. So just to complete yung story that this work that I've done during my PhD, yung first draft ng paper na to is ginawa ko pa ng July 2018. There are times that we were not able to do the revisions kaya nag-stagnate yung yung paper, but eventually finally we were able to revise it. It's also received rejections from other journals. So we tried to submit it in Nature Catalysis Journal, but after rejection, so they suggested that we submit it to Applied Catalysis B, and then finally it got accepted. Ayan. So just to show you, you can check itong journal namin, and with the help of our postdoc in the US and then my professors, we were able to publish it in the journal. Lahat ng figures na pinakita ko sa inyo and observations na ginawa namin is actually just summarized into 2 figures. So these figures are actually done by the postdoc, which is my co-author in this paper. So very helpful then if when you are publishing already that you have good skills in drawing and creativity, kasi nakakatulong talaga yun sa pag-produce ng mga maganda and clear na figures. Ayan. So ito din yung pinresent ko sa inyo, but in a different format since we have revised it for publication. Ayan. So to end my presentation, I just want to share ito mga takeaways ko in my PhD journey. So the first one is a good dissertation is a done dissertation. A great dissertation is a published dissertation, but there is no perfect dissertation. So for you to be able to get a good dissertation, kailangan nyo matapos nyo muna yung dissertation ninyo. And hopefully, you will get to publish it in a good journal. So for you to be able to finish, you need very important na aspect is yung focus. So you won't get anywhere without focus. So yung mga times na na-mention ko before na walang progress in the writing of the paper is because hindi ako nakafocus dun sa pagpapublish ng paper at that time. So kunyari, busy ako dun sa faculty duties ko. So nahinto yung aming work on the paper. So very crucial for you to get anything done, not only for your research work, but for anything. So you need to focus. And gaya ng sabi ko kanina, di ba, that you will get to the right station. Pero kung hindi nyo alam kung saan kayo pupunta, so hindi rin kayo makakarating doon kahit ano yung gamitin yung train. Okay? And then, do one step at a time. So there are times during my PhD that parang walang nangyayari tapos nadi-discourage ka. During that time, syempre nakaka-overwhelm na ang dami mong kailangan gawin pero you don't get anything done. So I suggest that do the smaller steps first. So kung ano lang yung kaya, unti-unti naman siyang matatapos. So at least kapag alam niyo yung goal ninyo and then you continue moving forward, kahit pa isa-isang step, you will get closer and closer dun sa goal ninyo. And then next is yung you reap what you sow. So this one is I always apply dun sa work ko na kung ano yung efforts mo ngayon, it will actually be fruitful in the future. So kung effort ka during this time, actually you will not see immediately yung fruits of your labor, but eventually after a year or two, tsaka nyo pa lang siya ma-feel. The same with the opposite, na if hindi kayo nag-e-effort ngayon, so after a year or two, so wala rin kayong makukuhang products of your labor. Ayan. And then lastly, none of us got to where we are alone. So, for example, itong publication na to will not be possible without the help of my co-authors and then the support of my advisors. So, minsan, very important din yung connections ninyo at saka yung paghingi ng help from others. So, if you have good connections and if you know the right people to ask help from, so that will really help you in your research work. Yeah. So, finally, so makaka-move on na ako or makaka-move forward na ako from this research work. After publishing this work, we are now preparing for another publication to continue yung topic na to. So, aside from looking at the effects of the alkali-metal ions for OER, we also have done experiment to include the effects of added anions. So, aside from the alkali metals, what happens if we add different types of anions, in particular, the nitrates? Kasi sila yung madalas makikita dun sa mga electrolytes of electrochemical processes. And then, currently, we have also 2 approved projects na kung saan involved ako. One is on fuel cells, the Cypher-Picari project. And then the other one, same as with Sir Ram, we also have a newly approved DOST NICER project program. So our program leader is actually from TIP, Dr. Reb Juanico. And then we have 3 projects. So one is from Dr. Reb, and then the second one is from me. So ito yung project 2, the renewed Edison battery with advanced cell architecture for high energy density application. So the Edison battery or the nickel iron battery makes use of locally available materials, nickel and iron, and similar to the lead acid battery. So it's an aqueous-based battery. It's not a new technology, but we want to improve it because of the possible advantages of using the Edison battery. Kasi as compared to the lead acid, it has higher cycling life. So mas long-lasting siya as compared to lead acid battery, which is good characteristic, especially dun sa mga remote applications. So, hindi kailangan ng maintenance. However, it still has drawbacks, which is yung magiging focus nitong project na to improve yung safety component niya since it involves nickel and iron. One of the reactions produces hydrogen. So, kailangan ng gas purging now and then. So it defeats the purpose nung high cycling life and no maintenance kung kailangan siya ng gas purging. Ayan. So yun yung magiging focus no project 2. And then the NICER program also involves Sir Joey. So siya yung 3rd project namin for advanced batteries naman. So our NICER program will institute the Center for Advanced Batteries. Ayun. And finally, I would also like to thank my advisors, Sir Joey and Professor Poya Abel Chuang, and my co-authors, Dr. Guang Fu, Mark, and my lab mates in UC Merced and in Lee. Yeah, so this research is made possible by the Green Power Program, ChemSusChem, and my DOST SEI Picari Scholarship. So you may now ask your questions, and thank you for listening.
Thank you so much. Thank you so much, Ma'am Julie and Del Rosario. Sorry for your talk with us. So, Dr. Del Rosario started her talk by recounting her PhD journey, and she hinted that sometimes things don't go according to plan, but that's okay. So, she initially focused on the ORR reactions. So that this was based on her experience in electrochemistry and inspired by her dream of contributing to fuel cell development for electric cars. But then she changed her topic to OER reactions, or oxygen evolution reactions, and she was then able to publish the results of her dissertation. So in the end of her talk, she highlighted the importance of focus in reaching our goals, and to take she advises us to take things one step at a time, and that we reap what we sow. So we better reap things that we like to sow. So she emphasized the importance of camaraderie, connections, and support from our peers. So she also, at the end of her talk, provided a glimpse of the future projects of the Laboratory of Electrochemical Engineering. So if you have any questions for Dr. Del Rosario, you can send them in using the live chat features of Zoom, or for live questions, please use the raise hand feature and wait until I acknowledge you before unmuting. So I encourage you to turn on your cameras while asking your questions live. So for our first question, since the first part of your paper was done last 2019, were you able to explore other alkali and alkaline earth metals aside from potassium?
Actually, yes. We tried working on alkaline earth metals. So I tried developing or synthesizing using magnesium and calcium. But unfortunately, the one I have shown, which is yung potassium dope, siya na yung best performing among the synthesized catalysts. So only limited it to the alkali metal group from then. If you have seen siguro yung presentations before by one of our lab members, so si Ace. So si Ace yung gumawa nung theoretical part nung experimental dissertation ko on ORR. So he is working on the theoretical investigation of these alkali metal and alkaline earth metal dope carbon materials. So far, dun sa results niya gives positive results. However, we have not yet confirmed them experimentally. So yun yung kulang pa dun sa to connect yung results niya tsaka yung results ko.
Okay. So this was the talk of Mr. Esteraon po, no?
Yes.
Tama. Okay. Right. So we have another question. Why do multiple steps in the reaction mechanism entail lower performance?
Okay. So that refers to the ORR reaction, no? Kasi if you have a complete reaction in ORR, yung complete reaction natin involves a 4-electron transfer mechanism. So it means that 4 electrons must be completely transferred before makapag isang complete reaction ng ORR. So if the number of electrons is lower than that, it will result to multiple steps, which is not efficient para dun sa reaction natin.
Okay. So the next question is, how does kinetic overpotential affect performance?
Okay, so yung overpotential refers to the non-idealities of your system. So kapag so yung potential is the energy that you need to apply in this case for the reaction to proceed. So kapag mataas yung overpotential mo, that means you have higher than the theoretical na energy na kailangan mong i-apply. So you are actually losing yung efficiency ng reaction natin if you have high kinetic overpotentials. Yan.
Okay. So we have a question here from the audience. So about your initial dissertation topic. So were you able to confirm the successful doping of potassium ion on potassium on graphene using other techniques such as X-ray absorption spectroscopy, XANES, and EXAFS?
Actually, yes. We did another test, but that showed na merong very small amount of the doped potassium on the catalyst, on the carbon material. So we did ginawa namin test, and another X-ray spectroscopy technique that we have used. But dahil very small amount ng potassium, so very small lang din yung signals na nakikita namin. So one of our recommendations in that part is to monitor or to check and to revise yung dopant to carbon ratio ng material namin para makakuha ng better results.
Another follow-up question to that is, what is the nature of the bonding or interaction of potassium with the carbon atoms of graphene?
In that case, I think yung doped siguro is di namin na-confirm whether ano yung type of interaction na meron sila. But we are sure na present siya on the surface of our catalyst material. Di lang namin na-confirm what type of interaction yung meron. Yeah.
Okay. So we have another question, a little bit more personal. How did you deal with the anxiety of changing topics? Do you have any tips for students who are experiencing similar problems right now?
Okay, nung time na yon, difficult kasi hindi mo sure kung ano yung magiging wala talagang clear plans if you change the topic kasi it's like starting again tapos noon with limited time as compared nung una kang nag-set ng proposal. Pero ano man ginawa ko doon? Since very limited lang talaga din yung time ko doon sa US kung saan ko gagawin yung experiment. So I focused more dun sa yung energy ko para matapos siya agad. So actually wala na akong time para isipin na hindi ko 'to matatapos, So inisip ko lang na kailangan ko 'tong gawin at matapos na para makauwi na ako. Ayun. Yan, actually nung time na 'yon, since I changed the topic and nabawasan yung time ko to do the work, I spend a lot of time in the lab. Since meron ding ibang gumagamit nung equipment na kailangan ko sa lab, so meron din kaming shifting. So there are times na nag-spend ako ng 15 hours diretso sa lab from morning till night. Tapos minsan naman kailangan ko mag-spend ng overnight dun sa lab para lang matapos ko siya. So once na magpalit ka ng topic, I think double time yung kailangan. In terms of the anxiety naman, instead of focusing on the anxiety, I think mas nag-focus ako dun sa kailangan ko siyang matapos. Yun.
So, kailangan po talaga ng malakas na mental fortitude.
Yes, that's right.
Okay. So, since you mentioned rin po the use of equipment, a question here is, how are you able to learn the different experimental techniques such as cyclic voltammetry? Can we learn these techniques in the department?
Yes, we have the equipment in Lee that are able to do these experiments. So just to give you a background kung paano ako nag-start dyan, nung una akong pumasok dun sa lab ko nung MS, wala talaga akong idea on electrochemistry. And since sobrang tagal na rin ng chemistry ko nung talagang inaral ko siya from scratch, how to properly prepare yung samples ko from getting them from the reagent bottle, to weighing, ganyan. Tapos noon yung different parts of the equipment, yan. So from the start, syempre, wala ka talagang alam. Pero once na na-exposed ka na and kailangan mo talaga ng mentor na magtuturo sa'yo. And then, syempre, pag alam mo na yung basics, so then you can start exploring kung ano yung mga possible gawin with the equipment and with the techniques as well.
On that note po, what advice can you give to researchers whose experiments are greatly affected by the pandemic since it is almost impossible to perform wet lab experiments at the moment?
Ayun. So, I think yung best actually is to have an alternative dun sa experimental setup. Kasi nga, limited yung pwedeng gawin in the wet lab. Or if hindi maiiwasan yung wet lab experiments, so dapat merong yung timeline for doing that should be minimized. And once nag-open or naging available yung lab, dapat makapag-set kayo agad ng date in the lab. So that means yung preparation part is crucial para maging smooth yung time nyo na spend in the lab if ever na makapasok sa lab. Pero yung best pa rin is to have an alternative which is probably kung computational method, ganun. Or minimize talaga yung amount ng time na kailangan sa lab.
Okay. So, do we have any more questions from our audience members? Okay, it appears we don't have any more questions. So thank you so much, Ma'am Julie, for your talk. Okay, so at this point, we would like to request everyone who are here to open your camera so that we can have a quick photo with our speakers. So please, everyone. Yeah. All right, so we have a lot of participants. So we have 2 pages. So may I request everyone to please smile just keep smiling so that I can get your photos. Okay, 1, 2, 3, and smile. We're going to the second page. 1, 2, 3, smile. All right, that's it. So, Sir Simon.
All right, so again, thank you very much to our speakers and to our attendees. So to conclude our webinar tonight, let us call on Dr. Jem Valerie Perez, our overall head of the DChE Seminar Series. Jem.
Yay, good evening, everyone. So again, it's really exciting to see 2 of our very own faculty members to achieve so much in their research careers kahit early pa kasi they're very young still. So very relatable din yung PhD journey ni Dr. Del Rosario. Anne del Rosario po, not San Jose again. Though magka-level naman because both are talented. So same din, I published my results from my PhD dissertation years after pa. And she's right in saying na not everything happens for a reason. And not everything happens according to plan, lalo na in terms of research na maraming factors that will come into play, but it's still okay, you will still make it to your station eventually, ganyan. But for Dr. Del Rosario, it's more than okay because look at her publication, 16 ang impact factor, so kahit 3 years in the making, di ba? Wow pa rin yung result. So I would like to also congratulate both of our speakers on their recently approved NICER projects. So these NICER projects have the department as co-implementing agency. So with these new projects, the research capacity of the department will surely be enhanced, and I can't wait to see more of their interesting findings and scientific contributions from these projects. So to formally close the event, I would like to thank also our moderators, Sir Rick and Sir Syme, for your kind assistance as always and for helping organize this successful event. So thank you also to our speakers again for tonight, Dr. Tamargo and Dr. Del Rosario. So despite their very busy schedule, may teaching, research, may admin work duties pa yung department chair natin, si Dr. Del Rosario. But they still share their time and their expertise with us. And meron pang pa-bonus na research and life tips as well. So lastly, I would like to thank you all for attending, yung mga graduating students, graduate students, and other guests for tonight, for your continuous support in all the organized events of the department this semester. So culminating activities that are in line this month are the undergraduate and graduate research colloquia. So I hope to see you all there as well. So let's all stay safe and let's have a fruitful week ahead. Good night, everyone. Thank you.
Thank you po, Ma'am Jem. So, thank you to everyone who attended our webinar. See you all on our undergraduate and graduate colloquia. Good night, everyone, and thank you.
Thank you, sir. Thank you, Ma'am Jem.
Thank you po, Ma'am.
Thank you.
Ram. Thank you po.
Thank you, Ma'am Jem.
Thank you rin po sa inyo. Salamat.